Hello, this is a quick overview over Tween 12's Mecha-Megalodon project. We're going to get into some introductions and project definition. Starting off with Meet the Team, my name is Trenton Praski.
I'm Keenan McKibben.
I'm Shae Rittenberry.
I'm Gregory.
And I'm Jason Jong.
Next to on the support team, our client for this project is Proportion Air, and helping us from Purdue side is Professor Garcia and our two TA Sukesh. Next, it's a problem description. So we've been assigned by Proportion Air to create a fabricated, life-size, fully pneumatic 9-foot shark, as well as fully animatronic. So kind of the three sections of this shark we did was tail, the head, and in the midsection. For the tail, it would kind of generate the thrust of the fully pneumatics, kind of generating the natural movement of the shark, as well as the head design and having the wide controls within the midsection of the design of the shark.
And then we're going to move on to the scope of work and methodology of this project. So the scope of work, just as we stated before, we're creating a life-size shark that's supposed to be functional through propulsion through the tail system and have electronics through the upper body and then the actuating jaw. And we want this thing to be real and look like a real shark. And then using resources provided by our clients and Purdue to be able to create the functionality of the shark. And then we also want to be aware of the safety as well as show learning opportunities that we are able to demonstrate using our project. And how we kind of go about this project is using a 5-step method: empathize, define, ideate, prototype, and test. We want to make sure we have all our design and documentation laid out before we went into the prototyping testing stage. As we kind of move into the manufacturing and tests, we want to make sure that we're able to demonstrate everything throughout the process clear and concisely.
So on to the state-of-the-art and design requirements. So this is some of the inspiration for this project and some of the things that we looked into while we were researching what's out there already on the market. On the left is Bruce, which you might already know from the movie Jaws. Fun fact, there were 3 different sharks used in the movie Jaws. There was the left shark, the right shark, and the main cinematic shark. And we were kind of able to take some of the animatronic inspirations from that design. And on the right there, you can actually see a more technical shark, which is better at navigating the ocean and bodies of water. That was created by Blue Robotics. And while it doesn't have an actuating tail, it does have a ballast system, which allows it to submerge and rise in the water.
The design requirements matrix is something we use to make sure we meet all the design requirements of this project. And this is done by saying design requirement, the design target, as well as the validation process. For the first line up there, we have the design requirements for the movement of the shark. So we want it to be self-propelled using tail propulsion, using pneumatics to create thrust. The second design requirement is to do with the appearance of the sharks. We want realistic shark anatomy. And for the validation, we want it to be able to be identified as a shark. For number 3, it's to do with the size of the shark, so greater than 4 feet in length, and we'd be able to measure it as validation. Number 5 would be to do with the jaw of the shark. Number 6 is about the performance of the shark and its ability to dive. So it should be fully submersible and should be able to be submerged under the water. Number 7 is to do with the camera vision system of the shark, and number 8 is again about durability and how waterproof the shark is.
Now on the system sub-solutions. So for mechanical design, the entire upper body subassembly of the shark contains the electrical box and ballast tank. This allows for your controlling and actual depth adjustment of the shark. And the entire tail subassembly contains the steering pistons, bullshit pistons, and caudal fin. This is what allows you to guide the shark and propel it through the water. Now for this ballast design, it consists of 2 5-inch stroke single acting cylinders, and you'll be displacing 1.28 pounds of water, allowing it to change density and rise and fall in the water. And the service level control console, it consists of a LED display, an e-stop button, 2 input buttons, a silent display, and a port for an external control that will control the shark through the water and turn it off when anything goes horribly wrong.
Moving on to the results. So as you can see here, this is some of the thought behind how the propulsion system in the tail works, and it verified that our design will work when we created it. So for every segment of the tail, we have 22.66 degrees for the first two segments, and then we have 24.44 for the latter two. So we actually were able to use some equations in SolidWorks in order to figure this out. And when we manufactured the tail, we were able to verify the range of motion needed to emulate a real bull shark, which is 90.2 degrees.
So the electrical enclosure will have a penetrator going through it, allowing for wires along with pneumatic tubing to go through this watertight container. And we wanted to test to make sure this thing actually works. So we left it inside of a container, filled it with water, left it for 48 hours while it was completely submerged, and verified that no leaks have occurred.
And finally, on this slide here, you can see two of our subassemblies, that being the shark head and the tail that was previously mentioned. So for the shark head, we wanted to print it much smaller than its actual size before we committed to printing it to scale. So we were able to successfully print it at a PLA, and we were able to test its range of motion of its bite. And then on the right there, you can see the tail subassembly. We were able to verify that the stroke length of 2.5 inches created the needed angle per segment that we needed to get out of the shark. Thank you.